Welcome everyone. For today's prep, we're going to start to look at some of our basic derivative rules. And we've seen a few of these already, but now we're going to kind of start to put all the pieces together. So the ones we've seen how to differentiate just a constant function all by itself, and then we've seen power rule, so how to differentiate powers of x. Now what we're going to do is we're going to see what happens if we, take a constant and try to multiply it with a power of x. Or what if we try and add and subtract different variable terms? So we're going to see the constant multiple rule, and we're going to look at the sum and difference rules. So to begin, let's just start with those elementary ones we've looked at before. So if we have a constant function, so our function f of x is equal to a constant k, and it's just k, there's really no variables here. Well, if that's the case, if we're trying to differentiate just a constant, the derivative of just that constant is 0. Remember, we want to think of derivatives as measuring change. So a constant function doesn't change. So, well, it's not changing. So the rate of change there is 0. Now, power functions, power rule, what happens there? So this is where we have x raised to a power r. And if we remember, power rule, we bring down the exponent, put it in front. We keep our variable the same. And then we subtract 1 from the old exponent. That's our power rule. So we've looked at these before. So what's new is our constant multiple rule and our sum difference rules. So let's start with the constant multiple rule. Let's look at this. So this rule comes around when we have a constant k times some variable stuff. So we have a constant k times a function f of x. So think of it as a constant times variables. All right. So what happens in this case? Well, we want to differentiate this whole thing. So what this rule says is we can first focus in on getting the derivative of just the variable part. So we can get the derivative of our variable piece there. And then that constant multiple that was in front just kind of stays in front. So the derivative works nicely with constant multiples. So it just kind of, the constant multiple just kind of gets bypassed. We just kind of gloss over it. So let's try an example. Maybe 2 examples. So let's look at the first one. Let's see how this process works. So for this first one, we've got a constant 2. So that's our constant multiple. And then we've got a power function x raised to the power 5. All right. So we want to differentiate this whole thing. Well, what this rule says is that constant 2 just going to stay in front. Just write that constant multiple. Then we'll put some parentheses. And inside the parentheses, we're going to compute our derivative of x to the power 5. All right, so we've got our constant multiple still in front there. And we're just going to differentiate the power function part. So when we do that, we bring down the 5, keep x the same, and subtract 1. And that's it. That's our derivative. Now, we could simplify this, and probably once you get the hang of this, that's what you would do. So we could multiply the 2 and the 5 together to get 10x to the power 4. Probably a little nicer to do this. But for right now, it doesn't hurt to show this kind of middle step. So another way to kind of think of this is when you do power rule, you're going to take the 5, bring it down, and then you can multiply it with the 2 that's in front there right away to get the 10. All right, let's try one more of these. So for the next one, we want to differentiate x cubed over 4. Now this one's a little different. It's not quite multiplication. So we want to rewrite this, get it in a nicer format there ready for our derivative. So what we're going to do is the way we're going to rewrite this, and a lot of times we do this with fractions, it's helpful to kind of break a fraction apart. So kind of separate off any constant pieces from your variable pieces. You kind of want to break things apart like that. And we want to reorder the function so that we have all constant multiple stuff in front, and then the variable stuff comes later on. So we're going to rewrite this as 1 over 4 times x cubed. So we're just rewriting that function in this format here. So it's like I'm taking the x cubed, I'm breaking it off of the fraction and putting it next door, and then we're only left with a 1 on top of our fraction then. Now the benefit of this version is now we have a constant multiple kind of sitting in front of our variable piece. So we're ready now to use our constant multiple rule. So again, the 1 over 4 is a constant multiple, so it just kind of sticks around in front. Then let's throw down some parentheses, and inside those parentheses we're going to compute our derivative of x cubed, the variable piece. So when we do that, derivative of x cubed, well, we bring down the 3, put it in front, keep x, and then subtract 1. And perfectly fine to leave it like this, but usually a good idea, multiply those constants together. And when we do it in this case, we get 3 over 4 with our x squared. All right, so that's the constant multiple rule. We'll save these other ones for class. All right, so we've got our constant multiple rule. Now let's look at the next one, our sum difference rule. So what this says is if we have a function f of x, either we're adding that or subtracting that with a function g of x. So this works for both addition and subtraction. So we just kind of put them together. But normally it would only be one. In an actual function, you're not going to see plus minus. You're just going to see either plus or minus. So what do we have? Well, we've got one variable piece, f of x, and we're either adding that or subtracting that with a second variable piece, g of x. And what we want to do is we want to differentiate that whole thing. Well, what this rule says is rather than trying to do the whole thing all at once, we can first focus on the first variable piece, get the derivative of that. Then, separately, we can get the derivative of that second variable piece. And then whatever operation was in the middle just kind of stays there in the middle. So if it was addition, it stays addition. If it was subtraction, it stays subtraction. So derivative works really nice with addition and subtraction. And the way you can kind of think of this rule is that the derivative we can just split up the derivative process wherever we see addition or subtraction. Now, one thing to be careful of, this does not work for multiplication or division. So if we have x terms getting multiplied or x terms being divided, doesn't work. Constant times variable is fine. But if we had two variables and we were trying to multiply them together, that's a different story. So we'll see how to handle that later on. So let's practice one of these. Let's do a little bit of our sum rule here. And we're going to look at just the first one. This function x cubed plus 5x. So when we look at this function, kind of see there's kind of two terms. So we've got the x cubed first, then we're adding, and then we've got this 5x second. So the way the sum rule works, we're going to calculate the derivative. So we'll call our derivative f prime of x. And what we're going to do is we're going to start by getting the derivative of that first piece. Then we'll get the derivative of that second piece. And we have this addition sign in the middle. So that addition sign is going to stay in the middle for our derivative. All right, so let's just start with that x cubed. Differentiate that. So this is just a power function. So we bring down the 3, keep x, subtract 1. So 3x squared. Now the 5x, this is a constant multiple. So the 5 kind of stays in front. And then we have to differentiate just the x. And derivative of just x is 1. So you can kind of think of that. When we're differentiating x, if it's just x, there's really like a hidden exponent of 1 there. So really it's power rule. So we bring down the exponent, put it in front, so we get 1. We keep x the same, and then when we subtract 1 from the exponent, we get 0. And our convention is that whenever we have something raised to the 0 power, it's equal to 1. So this whole thing is just equal to 1 there. So really, x by itself, really just kind of a special case of power rule. So another way to think of this, when we have just 5 times x, the derivative is just going to be the constant in front, the 5. And good to simplify this. We don't normally write multiplication by 1. All right, let's so we'll save it. We'll save the rest for class. So some good practice here, and we'll see you then. Bye-bye.